Welcome to the Inamena video tutorials on CSP technologies, Block 6, Unit 2, Definitions and Calculation of Efficiency. My name is Nicole Janot, and I have been working on CSP technologies at DLR for more than 6 years. My main fields of work are parabolic trough and component performance testing, as well as test evaluation and performance simulation. Starting with the motivation for efficiency considerations and a general approach to efficiency calculation, this unit introduces efficiency aspects relevant for concentrating technologies such as cosine loss, optical efficiency, incident angle modifier, and thermal efficiency. At the end of the unit, the main findings are summarized briefly. The efficiency of a process or device quantifies the degree to which it converts energy of one form to another. Hence, it is a good measure of the overall quality of a process or component with respect to the desired energy conversion. Thus, efficiency is a key figure for benchmarking of components, collectors, and systems used for concentrating application. The term efficiency is widely used by different parties of various backgrounds. A harmonized understanding is essential to provide a sound basis for discussion and decision-taking. Otherwise, differing points of view and assumed boundary conditions are likely to lead to various interpretations of the seemingly clear criterion. The main objective of this unit is to raise the awareness for the importance of the well-defined use of efficiency terms in CSP applications. In engineering, efficiency is generally expressed as the ratio of the work done to the resources used. It is the ratio of the useful output to the overall input to a system. This general definition is then refined according to the system under investigation. Typical subsystems considered in CSP applications are receivers, collector modules, collectors, or the entire solar field. These do not only imply different definitions of input and useful output, but also individual system boundaries and operation conditions. Potential differences in these assumptions and conditions may largely influence the actual value of the resulting efficiency. Thus, conventions for calculation are to be followed and assumptions stated clearly. This assures the usefulness of efficiency values. In the context of concentrating technologies, the solar resource is the crucial factor for efficiency considerations. Variations in irradiance cause changing operation conditions during testing. Every installation has an individual design point. Furthermore, different reference periods, like instances, days, or years, are possible. Starting from the total available solar input, the energy conversion steps relevant to parabolic trough systems are depicted in form of a Sankey diagram on this slide. The available input is calculated as the product of the aperture area and direct normal irradiance. At this stage, it is important to be precise about the aperture area used. In order to assure good comparability of results and focus on the concentrating qualities of the system, it is favorable to use the net aperture area, excluding any mirror gaps and other inactive areas, as the design of different collectors may vary largely. In the Sankey diagram displayed, the width of the associated arrows is proportional to the amount of energy or power converted. Cosine loss reduces the amount of effectively available energy for conversion at non-perpendicular irradiance. The cleanliness of a mirror facet and receiver glass envelopes further reduces the amount of available irradiation. The optical efficiency determines the fraction of available solar irradiation that is converted into heat at non-perpendicular irradiation. The incidence angle modifier accounts for additional optical losses at perpendicular irradiation. And finally, the thermal efficiency quantifies how much of the heat converted is actually available as useful heat of the field. Cosine losses are system immanent. Due to the single-axis tracking of parabolic trough collectors, the incident solar irradiance can only be normal to the aperture in distinct moments of a day. At all other times, direct normal irradiance is reduced by a factor equal to the cosine of the incident angle as illustrated by the equation. The incident angle and thus the cosine loss depends on the collector orientation and position of the Sun. The position of the Sun, in turn, is determined by the site, season, and time of day. For a chosen site at 36 degrees northern latitude, exemplary daily characteristics of the cosine of the incidence angle are displayed in the diagrams. The left one illustrates the characteristics of different seasons for a north-south collector orientation with comparatively little variation throughout the day, especially in summer. The diagram on the right shows the same characteristics for an east-west orientation of the collectors. This typically results in very narrow cosine factor characteristics with a distinct peak at solar noon. Considering the width and variation of the cosine factor characteristics, a north-south orientation is clearly more favorable at the given site in view of the total yield, the utilization of the installation capacities, and constancy of heat generation. This actually applies to most good solar sites. In a simplified approach, the optical efficiency of a parabolic trough is modeled as the product of the reflectance, transmittance, absorptance, and intercept factor. In order to understand this concept, we simply follow the path of the sun ray on its way to the receiver. For a focused collector, the incident solar irradiance is first reflected by the mirror facets. The higher the specular direct reflectance and the lower the absorptance of the mirror, the greater the fraction of irradiance that will remain after the step. On the way to the absorber tube, the redirected irradiance first hits the glass envelope, and the higher the transmittance, the less irradiance is lost at this stage. The absorptance characterizes the ability of the absorber tube to absorb and convert incident irradiance into heat. While reflectance, transmittance, and absorptance are material properties of the collector components, the intercept factor characterizes the quality of their geometrical assembly. It quantifies how much of the incident irradiance actually hits the absorber tube. Slope deviation in the reflecting surface and imperfections of the assembly of the structure, facets, and receivers can lead to considerable losses. In reality, there are of course multiple reflections and absorption processes, but this is a simplified model and a good approximation expressing optical efficiency as a function of basic surface properties and geometries. The incident angle modifier, abbreviated as IAM, summarizes angular effects in optical collector performance. It is derived from the ratio of optical efficiency at a given angle of incidence to optical efficiency at normal incidence. The contributions of cosine loss and IAM loss are compared in the graphical representation on the right. It shows the value of the modification factors as a function of angle of incidence. The effect of the cosine loss, indicated by the dotted gray line, is typically more important than that of the IAM, marked by the light blue line. Both effects combine to the dark blue characteristic. Because of the predominance of the cosine effect, the incident angle modifier should be separated from cosine loss. As an angular-dependent optical system efficiency, the incident angle modifier summarizes the effects of all angular-dependent characteristics other than cosine loss. This includes shading due to parts of the structure, like receiver supports, the drive, or concentrator gaps. Such shading results in moving non-illuminated spots on the receiver. Furthermore, optical properties like reflectance, transmittance, and absorptance are angular-dependent, and optical loss occurs at the end of every collector unit, as illustrated in the diagram on the bottom right. IAM characteristics are determined in code tests or by ray tracing. The thermal efficiency is mainly a characteristic of the parabolic trough receiver. The better its quality, the lower the heat loss at elevated temperature will be. A full thermal balance of a parabolic trough receiver, as shown on the right top, includes a large number of heat transfer processes between the ambient, glass envelope, and absorber tube. Therefore, it is rather complicated to model the balance analytically. Instead, empirical approaches are often preferred. Quadratic or polynomial approximations of the heat loss per meter length are common. The temperature difference between the mean receiver temperature and the ambient is considered the governing quantity. The graphic on the bottom right shows the specific heat loss per meter as a function of temperature difference to the surroundings for different levels of irradiance. The higher the irradiance, the higher the heat flux on the receiver tube, and thus its outer surface temperature will be. As the heat loss increases with the surface temperature, higher irradiance causes higher absolute heat loss. In testing, the thermal efficiency is calculated from the measured useful heat divided by optical efficiency, useful solar input, and cleanliness. Similarly to the empirical approach to thermal efficiency of receivers, the collector efficiency is commonly approximated by empirical equations. These combine optical efficiency and thermal losses and are expressed in terms of mean temperature difference to the surroundings. Rearranging the efficiency equation to express the collector performance in terms of specific heat gain allows to consider optical and thermal loss effects separately, which is beneficial for varying irradiance during testing. In the case of not strictly stationary testing, the heat capacity also needs to be considered. The parameters of such empirical models are determined from performance test data by means of regression or optimization. In performance testing, the thermal efficiency is measured in terms of the ratio of the useful heat and available solar irradiance. The useful heat is determined from measurements of the heat transfer fluid inlet and outlet temperature, mass flow rate, and specific heat capacity. The available solar input corresponds to the product of aperture area, direct normal irradiance, cleanliness, and cosine of the angle of incidence. These performance tests are usually carried out for a set of particular boundary conditions. These comprise the level of irradiance, angle of incidence, operation temperature, and collector cleanliness. Depending on the particular interest of the investigation, various systems, hence system boundaries, can be considered, ranging from a single collector or a loop to an entire solar field. This slide shows the results of power conversion and the Sankey diagram for an exemplary parabolic trough collector. It gives a basic idea of the relative magnitude of different loss mechanisms. For the chosen operation point, cosine loss and IAM loss are very moderate due to small angles of incidence. The same applies to the impact of cleanliness. As expected, the optical and thermal efficiencies are responsible for the largest share of the losses. According to the level of reference, the overall thermal efficiency amounts to values of 63.7 to 66%. Within this unit, various efficiencies to describe the behavior of parabolic trough collectors with respect to optics and energy conversion are defined and explained. In order to ensure a valid comparison of efficiency and performances, it is essential to be precise about the reference level and the effects included or corrected for in the consideration, such as end loss and cosine loss. Furthermore, system boundaries should be defined clearly. Measurement conditions like cleanliness or steady-state conditions, as well as the time base, instantaneous day, year, are to be stated. This brings us to the end of the unit on definitions and calculations of efficiency. Thank you very much for your attention.